Okay, let's get started. So last time we've seen the statement. Okay, we proved that every language in non-deterministic exponential time has PCPs with a polynomial amount of randomness, that means an exponential size PCP, and a polynomial number of queries. What was, from a technical perspective, the main challenge to prove this statement? The question.
Arithmetizing in a way that didn't require querying every point of the input or the constraint.
Yeah, so we want the verifier to run in polynomial time. So if the witness that we're writing down is at least exponential size, certainly its encoding also will be. And when we sort of transform equations about machines into equations about polynomials, that process has to run in polynomial time. Okay, so we saw something that I guess you might see being referred as a succinct arithmetization, meaning that we're doing it implicitly. Now I suggested last time that proving things about NEXP is sort of the way you try to make statements about delegation of computation. That's not quite true necessarily, because clearly we are not interested in statements about NEXP, because we can't make statements about NEXP in the real world, right? We never talk about problems of exponential size, we can only just reason about them. Really what we're interested in is, this was really just a warm-up to a parameterized statement about t-time non-deterministic computations, okay? And when t is exponential, it just forces us to think about the running time of the verifier. But in the parameterized world, which is the one that we really care about for the delegation of computation, here what we want to say is that we have a proof of polynomial size, or equivalently logarithmic randomness. We're going to make some number of queries that are exponentially better than the size of a non-deterministic witness, right? The non-deterministic witness here will have size t, because the non-deterministic Turing machine has t steps to make, so the witness can have size at most t. And crucially, the verifier runs in time that is polylogarithmic in t. And more precisely, actually, the verifier has to anyways read the input, so it will be polynomial in n, the size of x, right? And then you want it to be sort of exponentially faster than the running time of the computation, t, t of n, okay? Notice that this statement actually implies both of the prior statements, right? You can just set t to be any polynomial, and you will get this statement, right? And if you set t to be anything that is sort of a 2 to the poly, you will get this statement, okay? So this statement is actually strictly stronger than either of these, okay? It's kind of that's why it took us a while to get there, right? Because there is it contains a lot. The size of x. So when I say n times t, what we mean is that, well, we'll see it in a moment, but basically these are languages. You have a Turing machine M that runs where m of x runs in time t of x, okay? Size of x is n, and the verifier will have to look at x because it needs to know what thing it's checking, right? Okay, are there questions about why what we're doing today is sort of more than what we did last time? Now, as a statement, it is more, but what about the proof? It feels like what we did last time was kind of the right thing. Why wouldn't what we did last time, parameterized correctly, not work? Okay? Well, let's see that it doesn't work, actually. So why not we use same construction as last time? Well, let's just focus on one part of the proof. So I'm going to claim that the proof from last proof is overloaded. the probabilistically checkable proof that we would write down last time is too long. It's actually not polynomial in T. So what did we have last time? We had pi. Inside pi, we had the logarithmic extension a hat, right? And then we had a bunch of other sort of proofs, right? We had all these sum check proofs. Doesn't matter. I'm just gonna focus on this one for a moment, okay? So a hat was a logarithmic extension from f to the s to f, okay? And s was a parameter that came from the OSAT instance, right? So you will agree that the size of pi is at least the size of a hat, right? I mean, that's the first part of the proof, so certainly that's the case. And the size of a hat is what? It's at least f to the s, right? That we should agree. Now, we didn't really spend too much time figuring out the exact parameters last time, but as a ballpark, what do we expect the size of the field to be for soundness to hold? We are running sum checks, right? We're running sum checks over how many variables? So we had these two sum checks, right? One was over, what was it? R plus 3s variables. Another one was over s variables, right? In particular, we have a sum check over s variables. So it means that our soundness error in that sum check will be at least what?
S over f?
Yeah, at least s over f, right? Because remember, we pay something. At least 1 over f in each round of sum check. We actually pay more than that if we have the degree greater than 1. So this tells us that if we want to have any soundness, this f here should have size at least s. Okay? Good. So this is at least s to the s. Okay? Now, just for that sum check, okay? S to the s. All right. Now, what was s? S was the dimension, right, of, we were taking a hat to be the logarithmic extension of our witness, 0, 1 to the s, right? If we have a t-step computation, what do we expect s to be at least? If we have a t-step computation, we want to write the witness of size t as 0, 1 to the s. What will s be?
Log t?
Okay, at least log t. Okay, so that means that we have at least log t to the log t, right? But that's no good, right? That's super polynomial because, okay, one way to write it is that we have 2 to the log t times log t, right? Which is t to the log t, which is more than it's more than any polynomial, right? So that's a bummer, right? So the proof that we wrote down last time when we parameterized it in terms of t, it's of size that is super polynomial in t. Okay, it doesn't mean that still things work out for NEXP, okay? Because the way that exponents work, right? They behave a bit differently. So what do we do? Turns out that actually we don't have to literally reuse the same construction, but we can just do a small tweak on it. And really, we were just setting parameters a bit lousily last time. So what we're going to do now is basically go through the same proof as last time. This is a good thing because you see it a second time. Okay, that's an important proof to see and understand. We'll do it sort of rather quickly. And then we'll see how we actually should set parameters if we want the proof to be polynomial size. But does everybody understand why what we did last time doesn't work as is? Okay. All right. Okay, so our strategy, sort of idea, sort of, we're going to recycle same construction as last time. I mean, almost same construction, but different parameterization. All right. Okay, so let's do it. So let's recall first the definition of OSAT. Okay. It is the it consists of triples R, S, B. Okay. Where R and S are sort of integers, and B is a Boolean formula from R plus 3S plus, I think, 3, if I get it right. Yeah. And for which there exists this witness, for which we had this sort of exponentially many clauses hold. So for every W in 0, 1 to the R, for every V1, V2, V3 in 0, 1 to the S, you have B of W, V1, V2, V3, A of V1, A of V2, A of V3 equals 0. Okay? So this was the NeXP complete language that we used last time. Why did we mention it again this time? Because guess what? It's also n-time t complete. Okay? Now, we should make sure that it is n-time t complete with good enough parameters. Okay? We need to make sure that we can sort of go from n-time t to this language without a big blow up. Okay? We're not going to go through it. I'm just going to state a claim without proof. And the proof is basically the one that we saw last time, except that we keep track of parameters. Okay? So I'm going to say claim. There is a polynomial time reduction. Let's call it script R. Okay? Where for every instance mxt, so what's the instance mxt mean? It says, consider an instance of a Turing machine with an input x that you're asking whether it accepts within these time steps, okay? This reduction will create an instance of OSAT, okay? And we are interested in the sizes of these guys, right? So, and what's important for us is that R and S are both logarithmic in T, no more than logarithmic in T, and B is going to have size poly. Doesn't really matter the dependence on M, really, because it suffices to consider Turing machines of constant size. Okay, so syntactically, this is what comes out. R and S are logarithmic in T, and the size of B is a polynomial in the size of X and log T. Okay, and again, actually, the dependence on M is not so bad, but again, it doesn't matter because when you consider n time t, it suffices to fix some constant size machine. Okay, but this reduction so far is just outputting things. We need to make sure it is a reduction, so I just write it properly. Sort of, if m of x accepts in t steps, then RSB is in OSAT. And if m of x does not accept in t steps, then RSB is not in OSAT. Okay, that just means that it's a reduction. Anyways, what this is saying is that OSAT is n time t complete with parameters that are fine with us. Okay? The proof of this one is the same proof that we did last time. Okay, where you open up the Cook-Levin theorem, you look what's inside, right? But we're not going to do it again because it's not very interesting, okay? But it's literally the same proof. You just keep track of things, okay? All right, so this means that from the perspective of constructing this PCP, we know we can just start with an OSAT instance, and we know that the sizes of the objects that we're dealing with as a function of t are those written over here, okay? So this is all that we really need to remember when it gets down to, you know, checking that in the end we have a poly-t size proof. That's the important part. All right. Now, last time, once we had an OSAT instance, what did we do? Yeah, arithmetize it, right? And so the crucial thing was that we're going to arithmetize the descriptor of the problem, not kind of the equations themselves, right? So remember that B, the intuition for B is that it's not the clause itself, it describes the clause, right? And then also checks it, right? So we're arithmetizing directly this guy. So, and that's where the, if you could call it weakness of the proof was, we were arithmetizing it in a way that created this problem. So this time we're gonna pick parameters slightly differently. This setting of parameters is actually, I would say, important because it shows up in many constructions. I didn't make a big fuss of it. We used it already when we looked at doubly efficient interactive proofs. I just kind of set it like that, and I didn't make a big deal out of it, and you will see the same setting again. The same setting appears when you study coding theory, for example, in the Reed-Muller code. It's a very standard setting of parameters to make sure that your encoding has polynomial size. Okay? So let's see. Let's write it maybe here. So let RSB be an OSAT instance. And let F be a field. And last time we just had a field. Now we're also going to take a subset of the field that we'll pick it later. Okay? The subset that we used last time was 0, 1. This time it will be important not to use 0, 1, but to use actually a larger set. Okay? And the dimension, which last time was, we were using log t, like, you know, this, or rather just, we were just directly using s and r, okay? Now we're actually gonna use h to pick a dimension, let's call it m sub s, and it's gonna be s divided by log h. Notice that when h has size 2, then this collapses to their setting from last time, okay? So I'm going to pick a dimension m sub s and a dimension m sub r, which is r divided by log h. Okay? All right, so we can, so what does the lemma say? We can compute in a poly bh log f time an arithmetic circuit last time we called it b hat, so let me call it b hat star because we will be using the b hat from last time in the proof. So, but you know, b hat star is going to map f to the mr plus 3 ms plus 3 into f. Okay, so notice that I'm using, every time I would have used last time r, now I'm using mr, and anytime I would have used s, I'm using m sub s. Of total degree, poly in B and H, such that, okay, so when we say we arithmetize, we have two parts. First is what the verifier computes is the arithmetized kind of new descriptor, right? But then we have the witness, which was last time a polynomial, right? Of what degree? Last time we were taking a low degree extension of a function from 0, 1 to the s, right? What degree will it have?
2 to the s?
No, that's a bit high. That we have s variables, right? And so in each direction, we only have 0, 1, right? So it means that it will be multilinear, right? Because remember, when we're extending on a cube, we pay for the degree in each dimension, right? So this time, we're actually taking a bigger cube. We're kind of, instead of picking such a large dimension, we're going to reduce our dimension and pick up the side of our cube, okay? Because kind of the dimension was the problem, so we want to make it smaller, okay? So, so we're going to say that RSB is in OSAT if and only if there exists. Now this time is going to be a polynomial a hat from fms to f of individual degree less than h. Okay? Because now we're going to pick sides of the cube that have size h. And we had two conditions, okay? Maybe let's talk first about the second condition. What was the second condition that we were considering last time? Right, so OSAT has only one condition, but then when we arithmetized, we had two conditions, right? One was about what?
Make sure that it was 0 or 1 on the Boolean hypercube.
Right, and now on which hypercube do we want it to be 0, 1? So I didn't really say explicitly, but I'm sort of implicitly saying, why do we have this h? It's because now we're considering another hypercube, not the Boolean hypercube. We're considering which hypercube? My setting of MS should be very suggestive. For example, if I take h to the ms, what do I get? I will get something of size 2 to the s, right? So that sounds like my weakness. So that's basically saying that, right now I'm considering the hypercube h to the ms. So that's why here I want to say for every v in h to the ms, I am going to say that a hat takes Boolean values, okay? So basically I have this cube, right, of direction, where in each direction is h, right? And I'm extending it to the whole field, and I'm kind of putting inside here my 0, 1 to the s values of a. Okay? Before I was directly putting it in a Boolean hypercube. Now I'm just kind of rearranging them arbitrarily to just sit inside this other hypercube, whose dimension is smaller and sides are bigger. Okay? I still have to say that whichever way these points are laid out, they all still have to be Boolean. Okay? So I'm saying that here. Okay? I think some of you are like confused, so let's do that computation. So the size of HMS is what? It is size of h to the log s, right, over log h. Sorry, to the s log h, right? But that's the same as 2 to the s times log h over log h. So you see that the size of the h to the ms is exactly 2 to the s, right? That's why I'm picking it. Okay? And maybe to, yeah, but we don't have a choice of the field yet, so I'll do that later. Okay, so this is one condition. What was the other condition? The other condition had to do with the satisfiability, right? So what should I write here? Yeah.
For all w, v1, v2, v3.
Oh, yeah, hold on. W in what? In which domain?
H to the ms.
H to the what?
Sorry, h to mr.
Yeah, mr. Okay. And for every v1, v2, v3 in h to the ms. Notice that this mr, h to the mr, is some other some other cube, right? That has different size because W has started out with a different number of bits, right? R. And then we say, okay, B hat star of W V1, V2, V3, then A hat V1, A hat V2, and A hat V3 equals 0. Notice that because of the second condition, then we know that when each of these guys, because it's A hat on H to the MS, will be Boolean. Okay? Okay, we actually need to prove this lemma. Last time, it was a very simple proof. This time, it is almost as simple, but there's an extra step to deal with the fact that now our coordinates are actually not in the Boolean hypercube anymore. So, is the statement of the lemma clear? It's basically the same as last time, except that now we're using different types of cubes. Okay? Still has a satisfiability condition and Booleanity condition. Okay? Now, last time, how did we choose the arithmetization? We had B hat, right? So what did we do with B hat? So how did we obtain B hat from B? So we had a descriptor that was a Boolean formula, and then we wanted to construct an arithmetic circuit B hat out of it. What did we do? Yeah, we just kind of straight out, like opened it up, and you say, okay, here's an AND. I'll replace it with a times, right? Here's a not, I'll replace it by a 1 minus. Let's just do that, okay? So let's do it again and see where we go. So we can go from B to B hat via sort of, let's call it naive arithmetization. That's fine. Okay, now we have at our hand an arithmetic circuit, B hat, which it's not quite what we need, right? Let's even think about the signature. B hat, how many inputs does it have? It has a R plus 3S plus 3 inputs, right? Now, those last 3 inputs are pretty good, right? We expect to pass in the right stuff here, right? But this B hat star, it accepts these tuples of field elements, like for example, W, V1, V2, and V3, and they're kind of like overall, it's the correct number, but right now they're distributed in a different way, right? In particular, I am not even passing Boolean values anymore, right? Before, when we were quantifying W over the Boolean hypercube, I was literally passing either 0 or 1 to B hat, right? Now, like, I have that many number of elements, but these guys are, like, they're not necessarily 0, 1 elements, right? Because H could be the elements 0, 1, 2, 3, 4, for example, right? And sometimes, I might pass in, 3. I can't pass 3 to B hat. He won't know what to do with it, right? You see the problem? Like B hat does, when I directly arithmetize B hat, it's okay provided I pass in Boolean values. He doesn't understand what it means to reason about other field elements, okay? So this is a bit of a problem. But it's not really like a big problem. What we really want to do is to say, okay, fine, you pass me this one. I really just need to take out the bits inside W, okay? W is a sequence of MR field elements drawn from H. I take each one of these under the promise that it's from H, and I just need to take out the bits that it represents. I just need to kind of write a subcircuit that extracts the bits one by one. Right? This makes sense. I just need to do it in a way that doesn't take too many gates or too much degree. Okay? So that's why syntactically this is maybe the main difference besides changing the settings of parameters from the proof from last time, that we need to use what are called, or we can call projection polynomials. These are polynomials that will take a field element from a domain and spit out the bit representation, one of the bits of that field element under the promise that it comes from a certain domain, okay? And specifically, we're gonna let's call it pi I from F to F be the polynomial of degree less than h such that for every alpha in h, pi I of alpha is the ith bit of alpha. Okay? So I can definitely define this function, right? Because I can definitely define this polynomial because I can just define the function over h and extend it. Right? Over h, I can write down a function that does the right thing, and then I just extend it by interpolation. That's why the degree is less than h. Okay? Now, are we afraid of paying degree in h or paying work proportional to h? Well, it depends what we set h to be, right? Provided that h will be of polynomial size, this is okay to do, right? Okay. Okay, now we have that guy, okay? Notice, by the way, that this doesn't mean, just to make sure, what will this polynomial do if I pass in an element from the field but outside of h? Will it spit out a bit? Who knows, right? It probably won't, right? Its job is only to spit out bits when the element comes from h. That's why we can actually say that the degree is no more than h. Okay? He's not called to do anything outside of h. But we don't care because remember that here we're going to be considering to pass elements to b hat star only when drawn from h. Okay? Yeah.
Do we assume h is a power, the order of h is a power of 2, so that way pi I only has to consider one element, get the ith bit?
It doesn't really matter too much because already when in the Boolean case, maybe b hat didn't care about some strings of bits, right? Here, we can just assume that b hat will handle the logic, or rather b handles the logic and b hat sort of just does whatever b does. Good question. Okay, now with these guys, we can actually define b hat star. B hat star will take as input w, v1, v2, v3, and then some other sigma 1, sigma 2, sigma 3. And we will define it as follows. It's going to be b hat of, so I'm going to call this a, since sigmas was other things. B hat of what? So I want to take w, right, and split it into all the constituent bits and pass them one by one to b hat, because b hat will know what to do. So what should I write here?
Maybe like a big pi that represents spitting out the vector for each.
Yeah, okay, but let's not have too much notation. We can use parentheses for that, right? So we can say pi of, let me make sure I get my indices right here, pi I of wj. So remember, w is a vector, right? And now I have to do it for what? I have to do it for a j going from 1 to what? mr, right? Because I have mr field elements. And I goes from 1 to log h, right? I have that many bits. Okay, so these are the bit representation of w that b hat knows how to use, right? Then I pass in the same thing for v1, so I can write pi I of vkj. I do it for k going from 1 to 3, j going from 1 to ms, and I going from 1 to log h, right? And then, a1, a2, a3, I don't have to do anything. Those are single elements. And I know already that a hat on the cube will pass in Boolean things for me, right? That's it, really, right? I can just prepare I can just expect the prover to lay out things in the hypercube so that when I do all these things, he should do the right thing. Okay? And even if he doesn't, through this condition, this will make sure that all these things will be bits. Okay? All right. So, we forgot to say, so that's what the verifier does, and the honest prover prepares a hat, which is from fms to f, which is the low-degree extension of A. But now, I have to use the fact that there's a bijection between 0,1 to the s and h to the ms. Right? So really, the honest prover thinks of the assignment as just a function on h to the ms and just extends it. Okay? And that will give individual degree less than h. Okay. So is this clear? So the reason why we didn't do it all together last time is because there's some additional complications that. Anyways, the main point here is that because we set parameters differently here, then we had to introduce these projection polynomials, okay, to extract the bits for us. Okay, but now we're basically almost done because now we have a problem that looks a lot like what we did last time, right? So, let's just do what we did last time with, the modifications that are, the reason why we're going to go through it is not because there is anything interesting, just because you see it another time. But really, at this point, kind of all the new ideas are out, okay? Again, and the only idea was these two blue things. So both of these are vanishing problems. It's zero testing of low-degree polynomials, right? And remember last time we had a reduction from zero testing to sum check, okay? So we're going to apply that reduction again. Okay? So let's do it here. Maybe we do first the prover. The prover writes a hat from fms to f, which is the low-degree extension of a from hms 0,1. Okay. Then, for every mu in f to the mr plus 3ms, I think that's it. Here. Yeah, a proof pi1 of mu that q1 of mu equals 0. What was q1? That was a polynomial that is defined by, sort of together by b hat star and a hat, right? So this was sum from alpha in h to the mr plus 3ms, okay, of b hat star. We pass in w, v1, v2, v3, a hat v1, a hat v2, a hat v3, times something, we'll get to that in a moment. I'm parsing a as w, v1, v2, and v3. Again, b hat star will take all these things internally and apply projections and everything. Now remember here, there was this kind of bundling term, right? That was making sure that if I want all of these things to vanish, it suffices to consider the sum where these are the coefficients of a polynomial, right? And the polynomial was mu1 to the alpha 1 through mu mr plus 3ms, and then alpha mr plus 3ms. But this is not a polynomial. We had to extend it ourselves, remember? And last time we did a multilinear extension. This time we can't do multilinear extension anymore because the exponents, last time they were not 0, 1. I mean, they were 0, 1, but today they're not 0, 1 anymore, right? So instead of this, which is not a polynomial, we can just write its multilinear extension. Sorry, not its low degree extension, which I'm just going to write, and it's just an expression that you can check offline. Again, like there's nothing too interesting about it. It's a product from I equals 1 to. I just want you to see that it's something the verifier could actually compute himself. So first take a product on each variable, take a sum over h. A sum over h, that's fine, because this is cheap, that's cheap. And then here, it's mu I to the h, and then the indicator in h of. So what is this saying? Put in here this coefficient, and here is the delta function, the polynomial that is 0 everywhere in h and is 1 at h. Okay? And it does whatever it wants outside of this is the it's just univariate interpolation, okay? Doesn't matter. The point is that we're doing a sum check over this addend, okay, which is the product of these two things. Okay? You can verify this one offline that it extends that one. Okay? Doesn't matter too much. The point is the verifier can evaluate it. And the other one is for every mu in FMS, a proof pi2 of mu that q2 of mu equals 0. Okay? And q2 of mu was the other polynomial, the one for the Booleanity constraints. Now we're taking alpha in h to the ms. And the condition that we're going to look at is a hat of alpha times 1 minus a hat of alpha. And again, because we're doing a reduction from zero testing to sum check, we have to put in sort of this product, okay? Now this time is mu, or no, this is nu, nu I to the h, and then yeah, okay. Okay, this is the entire proof. Okay. Now, before we look at the verifier, we should double check that the proof has a polynomial size. I mean, that was the entire thing why we did this, right? So let's do that. Okay, but are there questions about what's in the proof? Again, I like the fact that in this lecture we're doing a lot of things that we did last time, because this is kind of like a some sort of capstone lecture of many things that we did about PCP theorem, and yeah, getting the verifier to run in sublinear time is an important thing to do. Are we fine with what's in the proof? Loading extension, sum check proofs for the first condition, and sum check proofs for the second condition, okay? So the size of the proof, let's check. Actually, by the way, we didn't even do it last time very carefully at all. So the size of the proof will be, well, let's count field elements. So I'm going to drop log f as a, so let's count field elements, not bits. The size of the extension is f to the ms. Agreed? I mean, it's just a table, right? Okay, how many of this bullet point contains a lot, right? So first you have to consider all possible mu's, right? So that's f to the mr plus 3ms, right? That's just fixing these, right? Then we are actually unrolling each of these sum check instances, right? How many rounds are there in this sum check instance? Yeah, mr plus 3ms, and in each round we pay a fan out of f, right? Because the choices of the verifier in each round are a random field element. So we again have another term that looks the same. Okay, and in each round we communicate a polynomial, right, of a certain degree. What is the degree of that polynomial? We have to pay for the coefficients that we're sending in that message. Well, the degree is the degree of this polynomial, right? What is the degree of this polynomial? Well, this plus that, right? What's this?
MR plus 3 MS plus 3?
No, it could be more than that. So inside b hat star, there is b hat. But inside b hat, there is b. B is whatever, right? So size of b. B was a Boolean formula, right? So here, we can really only say poly of b, right? Or really order of, let me be more precise. I can just be O of b. And then we also have contributions of h, right? You might think that h is an additive contribution, but actually we also have a multiplicative contribution of h because we're taking pi here and we're plugging it in directly into b hat, right? So it's really size of b times size of h. It's not plus, it's times. Because we are composing polynomials. We're taking a polynomial of degree h and plugging it into b. Okay? But it's okay. So it's polynomial in b and h. In particular, it is linear in b times h. And then we have this term, which is, if anything, simpler. We have m to the s choices of nu. We have m to the s rounds. And then here we'll have degree, a hat will have degree order of h, because that's what we're going to test. And then we have another h contribution here, so it will be order of h. Okay? So actually, tallying up all of the things in the proof looks awful, but actually is rather clean. Okay? Now, it still looks awful. The dominating terms here are really just two here. We should understand how does f to the ms behave, and how does f to the mr behave. That's really all that we need to understand. If you understand these things, then the rest is just a polynomial combination of the rest. Okay? So let's understand f to the ms. Okay? And this is kind of like, we'll check that our settings of parameters are correct. F to the ms is going to depend on the size of f, right? So, and now is where we should decide what is the size of f. Last time, we chose f to have size at least s, okay? This time, when you see the things that we need to do here, how big should we pick f? All right, let's start from simple things. This point alone, it will ask us f to be at least what?
Greater than ms?
Depends what we're testing. So we're testing individual degree, we don't necessarily care about that. Well, it depends which test we're running, but really the important parameter here is h. Right? Because we expect this thing to have the individual degree h in each dimension, so we better have a field like that express that degree. Okay? And then, if we're testing total degree, then really we need ms times h. Okay? Fine. But that constraint is always dominated by something that's happened here, because we're running sum check on polynomials of degree b times h. Right? And if you check, b times h is really like what dominates here, like the choices of f, because this one is only less, right? It's just h. So what this is saying is that our choice of f can be polynomial in b in h. In particular, they can be, let me just write order of b times h. what this tells us is that with that choice, we can figure out what is f to the ms. Okay? So if I do that, I'm going to say 2 to the ms, where we had a choice up there. It's s log h, right? And then we have log f, right? Now, log f will split into a log b plus log h, okay? And in general, even if we have a polynomial, it will still look like, you know, a constant times log b plus a constant times log h, okay? Now, the log h over log h doesn't really matter. So what matters is that we're going to have 2 to the order of s log b over log h, right? And by a similar computation, here is going to be 2 to the r, order of r, log b over log h. Okay? So this is telling us something. Remember that r and s are log t. B is going to be, you know, something, okay? Poly n and log t. How should we pick h? Remember, we haven't picked h either. So I want this entire thing to work out to be a poly in t, right? Can people see there? How should I pick h? Do I want b to stick around up here? I already have s, right? S is log t. That will already give me poly t. So a good way to choose h would be to say I'll just use it to kill b. Okay? Will it hurt me? Well, not really. Well, we need to check that the verifier doesn't care, but the verifier was anyways going to pay size of b. And it is going to pay size of h, but size of h is on the order of b. That's okay. Okay? So we're going to pick h to be on the order of the size of b. And with these settings, this one is going to be 2 to the order of s, which is polynomial in t. And this one is going to be 2 to the order of r, which is polynomial in t. Okay? So these are the settings that we pick with those dimensions to make sure that the proof has size that is polynomial in t. Okay? Again, last time, because we were doing everything for next, it mattered much less. Okay? Okay, I want to move on to something else, so we're going to only very briefly talk about the verifier. So we're not going to write it. Okay, let's talk about it. What will the verifier do? Well, the verifier will have to check each part of the proof. First, it will run a low degree test on a hat for individual degree h, or alternatively, it suffices to run a total degree test for degree h times ms. Okay. Then it will sample a random mu. Okay. That determines a proof it should inspect. That proof to inspect means that it's running a non-interactive version of the sum check protocol by traversing a tree. At the end of the tree, it will have to evaluate this polynomial at a random point. Okay? It has to evaluate this polynomial. That's okay. We chose h to have order of b, so it can do it. And mr plus ms, it's also something it can do. Okay? And this part, what is b hat star? That's just evaluating a bunch of projections and then plugging into b hat. B hat is just an arithmetization of b. Those are things he can do. Okay, so we checked that part. Our field is large enough, so we have soundness setter here. And notice that, like last time, we're accessing a hat at random points. We don't have to do self-correction. Then it will pick a random nu, okay, that determines a sum check instance. It should check. It runs the sum check protocol by traversing the tree. It gets to the end, has to evaluate this expression at a random point. it can evaluate this expression himself. And this part is one query to a hat, also at a random point. We don't need to do self-correction. Okay? So that's how the verifier operates. Is it clear? Hey, hopefully this time you've seen it the second time, we look sort of much more reasonable. Okay? Okay. So okay, let's remove this here. Okay, so what we've seen now is basically how to realize this picture. That's pretty cool, right? It's saying that for any n-time t computation, which corresponds basically to t-size proofs, okay? Any proof really that can be checked in polynomial time, you can encode it with something that is only polynomially larger, check it with an exponentially smaller number of queries, and also running time that is exponentially smaller. Okay, it's amazing. Okay, in fact, the paper that first introduced PCPs had a title. The title was "Checking Computations in Polylogarithmic Time." Okay, and it was really visionary paper. In fact, I'm going to write a quote from that paper that is sort of really forward-looking. It said something like, "A single reliable PC, like personal computer, can monitor the operation of a herd of supercomputers working with possibly extremely powerful but unreliable software and untrusted hardware." So this is a really like a visionary quote in a sense that already back then, so this exponential gap between computation and the resources to conduct a computation and the resources required to check it, there's an exponential gap. And so sort of a rather weak device, such as just personal laptop, could in principle, from a theoretician perspective, check much more expensive computations that wouldn't fit like in that machine. Okay. Well, the paper is linked from the website. I encourage you to look at it. You will see some of this. The way that we describe it is a bit of a sort of modern reinterpretation, but you should see some of the things that we've done in that paper. But now, as visionary as this quote is, there is also something missing. Okay, in the sense that it's kind of unclear how you go about and kind of use something like this. In a sense that, where is this proof written? Like, will you place the supercomputer in a soccer field and it spits out this very large proof? You print it like on the grass, right? And then the verifier is on the stadium looking at a few places, right? It feels like kind of unclear, right? How do you use it? This is qualitatively different than when we saw in interactive proofs how for bounded depth computations the verifier could check uniform circuit computation like in time that isn't, say, proportional to the depth but polylogarithmic in the size, right? There was a way to actually check it. You just show up to the verifier, to the prover, and you talk to him, right? And the number of messages, the amount of communication that came out from the prover, all these things was small, right? So that's okay. Now, a separate issue is whether you have time to be online to talk to a prover. That's a different story, whether you're willing to put up with interactivity, but at least there is somehow a procedure to do that. Here, there is also a procedure, but it's kind of awkward. Like, it requires you to write down the string, okay? And so, today, we're going to do about 20 minutes of cryptography. I'm going to, at a very high level, explain how you can use very simple cryptography and take something like this and basically turn it into a conversation, okay, that you can actually use. So they didn't talk about this. Somebody else sort of figured this out. That was a couple of years later. That paper is also linked from the website. So this brings us to the notion of succinct arguments. Before I maybe explain this term, let's try to do like a simple attempt at turning this idealized model into a protocol. So here there's a prover, there's a verifier, and now you might think that, okay, what's the big deal? Here's a protocol. The verifier will sample some randomness R for the PCP verifier. It will tell the randomness to the prover. The prover will produce a PCP string by running the PCP prover. And it will determine the query set that the verifier is interested in. Let's call it Q of R. Okay? And then it will send the restriction of pi to the query set, to the verifier. And the verifier will just sort of, it will run the verifier sort of using pi restricted to QR to answer. Now, what's the point? The point is that I'm sending a polylog amount of randomness, because we're using a polylog amount of randomness. That's okay. The prover sends back just the answers to the questions that I care about, not the entire string. Okay? So if I'm asking a small number of queries, I should get back a small thing, right? And then I check it. Okay? So there's a protocol. Okay? In fact, it's an interactive proof. Or is it? Like, does this make sense? Is this like a legit way of using a PCP? Right, some of you are shaking their heads. Why? Yeah?
Malicious prover can send you whatever it likes.
Yeah, it's like the verifier will always accept. Because the prover can make it accept, right? So the point is that probabilistically checkable proofs are proofs that are probabilistically checked, right? What does that mean? You first write down the proof, then independent of the proof, you sample your questions and you ask it, right? So if you choose your proof based on the randomness, then you can always fool the verifier. I mean, you can construct your PCP such that, right? Maybe you can, not always necessarily, but the point is that you don't have guarantees from the definition, right? It's maybe an analogy is to say that, say that we're playing a coin flip game, right? And the way we play it is first I flip the coin, I see the outcome, and then I choose my guess. It's like, it's not fair, right? So the point is that you first commit to your guess, right? Then you flip the coin. It's kind of similar to what's happening here in the sense that you first write down your proof, kind of you get ready with all the things, and then you sample your randomness, okay? So this doesn't work, but as stupid as a protocol it is, that's kind of what we want to do. And that's the only thing that we could do. What are we going to do, right? So we have to kind of prepend this protocol with another sort of exchange of messages where we get the prover to commit to the PCP he has in mind. Now, obviously he has to commit it without sending it to me explicitly, otherwise we're back to square one. By the time I read the entire PCP, never mind sampling, I could have read the entire witness without the polynomial blow up of the proof, right? So he has to commit to it first. And this is where cryptography comes in, okay? So a better attempt So this uses the notion of, oh, I should also say that, no, okay, we'll come back to that later. This uses the notion of so-called collision-resistant hash functions. Okay, I'll just write the definition because it's maybe makes it clearest. We'll say that a family of functions indexed by a seed is collision resistant if for every probabilistic polynomial time adversary, the probability that for a random seed of length k, the adversary, given the specification of the seed which actually specifies the function, outputs x and y such that x is different than y, but h of s at x equals s of x at y is negligible in k. Negligible in k just means very small in k. So this is the definition of a collision-resistant hash function. This may or may not sort of, the reason why I'm writing it is not because we're going to use it. I just want to tell you that in case you haven't taken courses in cryptography, one can write formally what it means to be collision-resistant. It just says, pick a random function from the family, tell the adversary what function you have in mind, challenge it to find two distinct inputs that match to the same output. If it's hard for him to do that, then that's collision resistant. Notice that we do have to have a seed because otherwise the adversary could have been born already with collisions in its head, and then obviously can output collisions, right? Now, given such a thing, the main construct of interest to us is the notion of a Merkle tree. Now, by raise of hands, how many of you have heard of Merkle trees before? Presumably, most of you, right? So Merkle trees is just a way of using hash functions that compress. By the way, hash functions that are collision resistant are interesting precisely when they compress. Otherwise, take an injection. There's no collisions then, obviously. Is a way to take a long string and you pairwise hash it until you get a so-called root. Okay, I'm going to draw it in a moment. Okay, so this is what's going to be used by the prover to commit. So let's do that. So so now the first message is going to be the verifier that samples a seed for the family and sends it to the prover. Now at this point, the prover, what really the verifier wants is a commitment to the PCP. But the prover is going to commit in a specific way that is going to enable local decommitments later. Okay, because you want to reveal only parts of the string later. One way to do it is to say, construct your PCP like you did before, and now pairwise apply the hash function to form a tree until you get a root. Okay, so say take adjacent things, apply the hash. Take adjacent thing, apply the hash. And then he commits to it. Okay, now forget the fact that it's a Merkle tree for a moment. Just the fact that the function is collision resistant means that by the time the prover has sent the commitment, he's stuck, right? He will not be able to just find some other things that go to that commitment. Okay? Now, the verifier sends the randomness and it says, okay, here's my randomness. The randomness determines a query set, say, I don't know, this location and say this location for a moment, this location and maybe this one. Okay? And like before, the prover is going to send back the answers, but then it has to justify these answers. It cannot just say, here are my answers, right? It has to say these answers have something to do with the thing that I committed before. And the structure of this tree allows the prover to certify the answers against the previous commitment. How? Well, you take the so-called authentication path for each of the desired leaves. Namely, you supply, for example, for this guy, you say, okay, you want to know that this guy corresponds to that root. Well, let me tell you this value, the sibling, this value, and this value. Why? Because given the black value and the blue values, you can reconstruct the root yourself. Okay, so you always pick the sibling of the level you're at. Okay? So this was the example for this one. For this one, it would be, take this one, and this one, and this one. Okay? Crucially, the authentication paths are small because the height of the tree is only log t. Okay? So you also provide the so-called authentication paths for the leaves in QR. Okay? What will the verifier do? Now it will check the answers using the PCP verifier, and then it will check that CM is consistent with the authentication paths and the values. Okay? Now, let's make sure that the verifier throughout this entire process still runs in polylog t, or more precisely polylog t and poly k, right? Because now we also have a security parameter that sort of comes from cryptography. He has to sample a random string. Okay, that sounds easy enough. He sends it. Gets back a root. Well, it depends what the size of the root is. Well, you pick this hash function to outputs, k-bit outputs, where k is your security parameter. Okay, so that's also easy. So that was k-bits, this is k-bits. So far, so good. The verifier has basically done nothing. He's sampling randomness. That's okay. That was polylog t. Now he gets back those polylog t answers, and for each of them, a log t size authentication path. Overall, that's a small amount. In terms of work, again, so far he was barely doing anything. At the very end, he has to run the previous PCP verifier, which if it is fast, then it's still fast because you're running it, right? And then on top of it, for each of the queries, it has to check the authentication path. But how bad can that be, right? You're just taking the answer, the authentication path, and you're hashing up. That's log t hashes, right? So overall, this entire thing will run in poly k, n, and log t. Okay? Now, this type of construct is known as a succinct argument. Now, succinct here denotes the fact that communication and verification time is sort of exponentially faster than plain computation. But what does argument here mean? Why not a succinct proof? Well, here it denotes the fact that suddenly we are using cryptography. We're relying on cryptography to prevent the prover from cheating. And we have lost something that an information theoretic property. In particular, we don't have soundness anymore. If the prover had unbounded power, then it could just create whatever collisions and cheat. Okay? So our notion of soundness right now is something that is called computational soundness. It could be that a prover could cheat us, but in order to do that, he would have to run in exponential time or super polynomial time. Okay? But that's okay, right? We don't mind. Because we only care about sort of polynomial size provers trying to cheat us. And actually, this is also inherent. We've seen early on in the class a lecture, Interactive Proofs, telling us that interactive proofs can't have small communication. Right? So it was, I don't know if it was the third or fourth lecture, we looked at a set of results from Goldrake and Hastad, which imply that, for example, we should not expect, or rather, if we have an interactive proof for n time t with communication little o of t, then can decide n time t in, I think it was like bp time 2 to the little o of t, which is something that we don't expect to happen, okay? So, computational soundness for succinct types of proof systems is necessary because for plain interactive proofs where we have statistical soundness, we cannot expect compression of communication relative to the witness size. Okay, this is something that we saw. We already proved this, okay? But okay, so we have to give up something. The thing that we give up is statistical soundness. Now we have computational soundness, okay? And we just rely on cryptography, and that's fine. In the real world, what actually happens is you will pick your hash function to be actually some pretty simple construction like SHA-256 or AES or something like that, right? So these are rather fast and a sort of non-complicated pieces of cryptography, and you use them for hashing things above the PCP. Okay, does this make sense? By the way, you might wonder, oh, but now there's interaction. I didn't like interaction to begin with. I don't believe interactive proofs are also usable because there is interaction. Look, it depends always on the application. And anyways, all of these things, that's public coin. All the things we've seen earlier in the course are also public coin, most of them. And there are other techniques to basically take all these public coin interactions and kind of make them a non-interactive message. So cryptography basically is used as a way to take many of these idealized models and turn them into things you can actually use, okay? I should also say that this construction is actually quite interesting in that while we do in the area of succinct arguments, which again we don't talk about too much cryptography in this course, but one of the there are various important goals in succinct arguments. One of them is making them efficient so you can use them in the real world. Another one is not only make them efficient, but make them so that they're post-quantum, so that all the effort that goes into realizing them actually sticks around for a longer period of time rather than maybe half a century or something. This particular construction, or something very close like it, is one of the leading candidates of something that is a post-quantum succinct argument, precisely because it doesn't use anything other than just simple cryptographic hash functions for hashing, basically. Okay. All right. So, okay, this concludes a section of the course where now we actually know how to delegate computations using PCPs. Okay, any n time t computation. Next week we'll do a short interlude on hardness of approximation. Why? Because I want to justify why does anybody care to reduce further query complexity, which is what we'll have to get later. What we want to do is to go beyond polylog t and achieve constant query complexity, okay? Which is even much less than that, right? And so in hardness of approximation, that's very very important. But I also want to say that even here it's important. While you might argue on the one hand, yes, the verifier is already working in polylog t, why should it care if it reads a message that is of length polylog t or not? Well, the reason is that once you compress this down into non-interactive proof, what people actually want to do with these things, they want to stick them, say, on a blockchain, for example, okay? And if you put these things somewhere and they're kind of replicated many times and stored forever, then it's not like one verifier will pay this polylog cost. It's like everybody pays the cost of storing them all the time, and those are many people. Okay, so reducing query complexity even in the delegation setting is well motivated on its own. Okay, so reducing query complexity is hard. Okay, so we'll have to get even sort of more complicated constructions. So we're going to need at least two motivations to have the strength to go through those complicated constructions. So this is one motivation, and next week we'll see another motivation for hardness of approximation. And then our next goal will be to achieve constant query complexity. Okay? Okay. Great. There are Piazza posts now about the final project. If there are questions, ask me.